All right, so we've learned how to take derivatives a little bit, not a ton, but we've learned how to use at least the power rule, the product rule, the quotient rule, take derivative of a constant, and use the reciprocal rule. So now we're going to talk real quickly about 4 reasons why a derivative might not exist at a point. So there are 4 reasons why a derivative wouldn't exist at a specific point on a graph or on a function. The first of those is if we had a corner. So a graph that looks like this, it has a sharp corner in it. What kind of graph gives us that?
Absolute value.
The absolute value is one that does often, well, it always gives us one. This particular graph is the absolute value of x graph. But it also could be like a piecewise function where I had a linear piece and then another linear piece. So it doesn't have to be like this perfect 90-degree angle. It could be any angle, just as long as it's a sharp corner from a linear piece to another linear piece. The derivative wouldn't exist at that point. Okay? And why would that be? What do we think? Because what's the
tangent line can be like multiple things.
Right. From the left-hand side, the slope of the tangent line is -1. And from the right-hand side, the slope of the tangent line is +1. And, well, what are derivatives? Derivatives are just limits, right? The slope of the tangent line is really just a limit. And if the limit from the left is not the same as the limit from the right, well, then that shouldn't exist. That makes sense to everybody?
So that'd just be at x equals 0. Like, say, if you were to find the derivative at x equals 1, that would exist?
Correct. Yep. The derivative of the absolute value of x at x equals 1 is just 1.
Okay.
Right? Or at 20, it's just 1 because it's still 1. Slope of 1 there. That's correct. All right. The next one is a cusp. You may or may not have heard of a cusp, but this is a cusp. It comes to a point. It's curving into that point, though. Okay? And the derivative does not exist at a cusp either, and I think we could probably see why. I mean, as we approach here, what is this derivative from the left-hand side going down to be close to? The slope is
0.
Yeah, but it's not becoming 0. It's becoming undefined, but it's coming to undefined from a negative slope, right? It's going towards negative infinity. And not 0, because 0 would be like a local max or min, like a horizontal piece. But from the right-hand side, that slope is positive, right? So it's going up towards a positive infinity value. And so this is called a cusp, and a derivative can't exist at a cusp either. Anybody know what this graph would be? Nobody knows what this graph is? Oh man, we'll have to come back to that in a second then. This one has a vertical tangent line here at x equals 0. Same thing, the derivative from the left is going to positive infinity, but from the right it's going to negative infinity. So at a vertical tangent line, you also don't have a derivative. The derivative doesn't exist at a vertical tangent line. Anybody know what this graph is?
Logistic.
Okay, it does look like a logistic graph, and a logistic graph could have that vertical tangent there. This particular one's not a logistic graph.
Is it the inverse? Sorry, is it the inverse of a cubic?
It is. It's the inverse of a cubic. Yeah, this is cube root of x, or it's or x to the 1/3. Yep, that's exactly right. So if we know that this one is cube root of x, any thoughts on what this one might be?
Is it the square root of the absolute value of x?
Square root of the absolute value of x. It would be close to that, but the square root of the absolute value of x, square root of the absolute value. Now, yeah, that's close, but that one will look slightly different. that one, what does that look like? It should be, yeah, it should be about the same. Yeah, you're right. That'll work too. That's not what I had in mind. But we could say that's the square root of the absolute value of x. I had in mind x to the 2/3 power, but that works too. Okay. Something like so a cube root, but then squaring that cube root, or also square root of absolute value of x. That's a good one too.
And is that third graph, is it undefined because the slope is like undefined? It's straight, it's like vertical. Is that why you can't find the derivative?
That's one reason why. The other reason is that from the left-hand side, it's actually, yeah, that is why. Yeah, because from both sides of this, it's positive infinity. I think I said it was negative infinity from one side and positive from the other, but this is positive infinity on both sides. But yeah, that's a vertical line there, and so it's undefined because that would be the slope of the tangent line would be undefined. So the derivative doesn't exist. Correct. Everybody good with those three?
Yep.
All right. Okay. And then the last one is if the original function has a discontinuity. Well, that's, I think, pretty self-explanatory. If the function doesn't exist at a point, then how could it have a tangent line? Like, we couldn't find the slope of the tangent line at that point because there's no tangent line because the function itself doesn't exist at that point. So anytime there's a discontinuity. So you want to memorize those 4 reasons why a derivative might not exist. And as we go forward through the year, we're going to look at some of the graphs of functions and ask ourselves, where does the derivative of this particular function not exist? You'll use this information to figure that out. So, good?
Yep.
All right, another small piece of information that we need is how derivatives work with motion problems. So we're going to do a lot of stuff with motion problems. We're going to do a couple basic ones today, but then as the year goes on, especially when we get into what would normally be like second semester, but I don't know when that'll be this year. Might make it sooner. We'll do a lot of motion problems. So if you have a function that is given as a position function, the derivative of the position function should equal the velocity function. And hopefully that makes sense, because how do we determine how something moves? Its rate of change of the position of, let's say, your car is the velocity at which you're driving your car, right? The rate of change of your position is velocity. Would you guys agree with that?
Yeah.
Yeah. So, and
Yeah.
what is a derivative? It's just finding us a rate of change at an instant. So if you take the derivative of a position function, it will tell you exactly how fast that car or the particle or you are running or something like that. It'll tell you exactly how fast you're going at that instant if you know a function that models your position. And we talk about acceleration, right? Well, acceleration is how we measure a change in our velocity, right? If I'm accelerating in my car, it means that my velocity is speeding up, right? Or if I'm hitting the brakes, if I'm decelerating, my velocity is slowing down. So acceleration is just a change in the velocity of your function. And so it's the rate of change of that velocity. And so the derivative of velocity should equal an acceleration function. And we could continue on with these. If you take the derivative of acceleration, you get this thing called jerk, and not like the person next door to you that you hate. It's called a jerk function, and it just represents a sudden change in acceleration. And we could actually continue going down this list. Anybody know what the derivative of jerk is called? What a change in the jerk of something is? Nobody? It's called the jounce. Okay, so the derivative of jerk, which you're not going to really need to know that, is called jounce. And sometimes they like to call jounce something else. Anybody, since you didn't know what jounce was, I'm guessing you probably don't know what the other name for jounce is. It's snap. You're not going to be tested on this. You're not going to need to know this, but it's fun, and you're going to appreciate that I've done this in a second. Guess what the derivative of snap is? Come on, guess.
Crackle.
That's right, it's crackle. Now, guess what the derivative of crackle is?
Pop.
Pop.
No kidding, it actually
No
is.
way.
Yep. So the derivative of jerk is jounce, which is sometimes called snap. Its derivative is crackle. Its derivative is pop. Guess what the derivative of pop is? You got to think back to like bad music that I hate. What's that like song from a while ago? So they're like some stupid song, like there was some dance to it or something. I don't even know. Maybe you guys are too young for this now. Like 5 or 6 years ago, people knew about this.
Whip?
No. It has to do with pop though. Whip is
The
that other
Mayday?
one. No, not that. Oh, I don't know. Maybe these are the same thing. Isn't there a thing that's like pop, lock, and then what do you do after that?
Pop.
What?
Drop.
Drop, right? Isn't that a thing? I swear that's a thing. Isn't that a thing? I don't know how to do it, but isn't that a thing?
So
Or
Yeah. So you
Yeah.
have snap, crackle, pop. Then the derivative of pop is lock. The derivative of lock is drop. And then the derivative of drop is shot. And the derivative of shot is put. So like a drop shot, you know, like tennis or something, a drop shot, and then shot put. I don't know. I don't know why those are what they're called, but that's what they're called.
But
You're never gonna
why?
need to know. I don't know. I wish I could tell you, but that's just what somebody decided to name them.
How? What does it even represent at that point?
Well, the put is the sudden change in the shot, which is the sudden change in the drop, which is a sudden change in the lock, which is a sudden change in the pop, which is a sudden change in crackle, which is a sudden change in your snap, which is a change in your jerk. I mean, it's there's so many tiny little factors that could be thrown in here. If you think about like, I mean, just going down to like jounce. Suppose we're accelerating in our car, and we're going up over a hill, and as we go up over the top of it, we crest that hill, even though we're pushing down on our accelerator at the same speed and should be accelerating at the same rate. As we hit the crest of that hill, we have a sudden a change in our acceleration, so that's our jerk. And then suppose as we're doing that, we hit a pothole in the road. Well, the pothole in the road is going to give us a sudden change in that sudden change of our acceleration. So that's going to be our jounce. And then suppose something small happens to affect that. Well, then that's the next one, and so on and so on and so on. The likelihood of you ever having to deal with any of those is pretty much a zero, of you ever having to deal with anything past jerk. But, snap, crackle, pop, lock, drop, shot, put, it's kind of fun. So that's what the derivatives are. So I thought I should let you know, just so you're informed. Everybody good?
I'm still not sure if you're joking us or not.
Oh, no, I'm not joking you. I'm very serious. Clearly, you're still not sure, but I mean, you can't see my face, but because you can see the screen, but I'm very serious.
Okay.
Yeah, you guys don't know me very well, but I never joke around, ever. Ever. Never. That might be a lie, but the rest of that was true. Jerk, snap, crackle, pop, lock, drop, shot, put. Let's take a look at this motion problem. I am serious. Those are actually what those are called. So we've got a position function here. S of t is equal to t squared minus 4t plus 3. We want to first find the displacement of the particle in the first 2 seconds. So what does displacement mean?
Change in position.
It's just a change in the position, right? So if we figure out where the particle was at t equals 0, and then figure out where the particle is at t equals 2, that should tell us the displacement, right? This should be s of 2 minus s of 0. Yep. So what's s of 2?
Yep.
S of 2 should be 4 minus 8 plus 3 should be negative 1 minus our 0 value, which is 3. So it looks like we went from 3 to negative 1. Negative 1 minus 3 gives us negative 4. The negative sign tells us that the displacement was in which direction?
The left.
Yep. So we've moved 4 units to the left in those first 2 seconds. No calculus needed there, right? Just terminology about the displacement. We're going to get to the calculus stuff in a second. Suppose we wanted to find the average velocity of the particle during those first 4 seconds. First 4 seconds, not the first 2 seconds. So the first 4 seconds. How would we do that?
Take the derivative of the position function.
Okay, so not yet. We're looking for an average velocity. So how do we find? Yeah, how do we find an average velocity thing? An average velocity should just be a change in position
over time.
Right. Change in position
displacement over time.
Yeah, displacement. It's a change in the position because velocity. I got so excited about Snap Crackle Pop, I forgot to mention this other really important thing. That we talk about speed. Speed is the absolute value of velocity, which tells us that velocity has direction to it. Right? A velocity has positive or negative. I could be going 5 miles an hour or negative 5 miles an hour. I'm talking about velocity. 5 miles an hour is 5 miles an hour to the right. Negative 5 miles an hour is 5 miles an hour to the left. Okay. Whereas speed has no direction. So if I say that I'm going 5 miles an hour, I could be going 5 miles an hour to the right, 5 miles an hour to the left, 5 miles an hour straight up into the air, 5 miles an hour in any direction. There's no direction to speed. So when we talk about an average velocity, that has to do with both positive and negative values. And so we want to make sure that we're doing displacement, not total distance traveled for this. So the displacement in those first 4 seconds should be s of 4 minus s of 0 over 4 minus 0. So what's s of 4? If you plug in 4, what do you get?
11.
I disagree.
Isn't it 3?
Should be 3. Right, 16 minus 16 plus 3 should be 3.
Oh, whoops. Never mind. I was thinking 16 minus 8. I was stuck on the 8 for the second.
Yeah. That's okay. Life will go on. So we end up with an average velocity of 0 units per time period. What is it? We got, I don't know, something per second. Meters per second. So 0 meters per second was our average velocity. But if we are interested in the instantaneous velocity, this is the velocity at a specific instant, then we want to take the derivative and actually find the velocity function. So v of t is equal to s prime of t, which should be 2t minus 4. And if we want to find that at t equals 4, then we'll evaluate it at t equals 4 to get that at that exact instant, we are moving at what speed?
4.
4 meters per second. Good or no?
Good.
All right. What about the acceleration at t equals 4? Well, we can find our acceleration function by taking the derivative of the velocity function, which should just be 2. And if we evaluate 2 when t is 4, if t is 4, what's 2?
2.
It's just 2, right? So 2 meters per second or meters per second squared should be our acceleration. If I asked you what is the acceleration of this particle at t equals 1,000, it is still 2. If I asked you what is the acceleration at t equals half a second, it's still 2, right? No matter what, it's going to be 2 because all of our variables fell out when we took that second derivative. Everybody good with that?
Yep.
Okay. Now it says describe the motion of the particle. We'll worry about that later. But we will also know, when does the particle change direction? So at what values of t does it change directions? So let's think about what that means. What is it? What's going on with our function, or with our velocity when the particle changes directions?
It becomes negative.
Right, it's either going to go from being positive to negative velocity, or the velocity is going to go from negative to positive. Right, so for the particle to change direction, we have to have a sign change in the velocity. And in order for that velocity to have a sign change, to go from positive to negative, what does the velocity have to equal for an instant there?
Zero.
Has to equal 0. So our velocity function was 2t minus 4. So we'll just set 2t minus 4 equal to 0 and find out that at what t value does it change directions.
2.
T equals 2 seconds. Everybody good with that?
What if it just touches 0 and then goes back in the same sign direction and it doesn't change signs?
All right, so we know that it did, and so this is something we are going to focus on. We'll prove it right now, so that's a good point. I should prove it. We know that it did change directions based on what we were doing earlier, right? We know that it started off at 3 and it went to -1, but then we know that later on it had a positive velocity. So we know that it started with a negative velocity to go from 3 to -1. And later on it had a positive velocity. So we know that it must have changed directions there at the only place that it possibly could have. But yeah, so it's, and as we get more into the applications of derivatives, we'll note that we'll want to make these sign charts. And so we'll put 2, our value, onto a sign chart and plug in a value greater than 2, for example, 3. Plug in 3 to your velocity function, and what do you get? You get something that is positive. True?
Yep.
Yep. And if you plug in something less than 2, like 1, you get a negative. And so we can see that at t equals 2, the velocity was 0, and to the right of that it was positive, and to the left of that it was negative. Good?
Yep.
All right, cool. Oh, and I said we were going to describe the motion. We've kind of done that. We know that it starts at a position of 3 right here, and it starts off by moving to the left, and it's moving to the left at a constant acceleration of 2 meters per second squared. So that means the velocity is increasing. And we know that at t equals 2, it stops moving to the left and starts moving to the right with a velocity that increases forever for all values of t. So That would be a pretty good description of the motion of that particle. Any questions on that? We're going to do some far more complicated ones eventually, but
So when you say that the average velocity is 0, it's basically because at those 2 points it had the same like y value, so technically didn't go anywhere.
that's correct. Yep.
Okay.
Its displacement was 0, and a change in displacement over a change in time is your average velocity. If you were looking at average speed, your average speed is the change, that's the total distance traveled divided by the total time, if you were looking for an average speed.
Okay.
But we don't quite have the tools yet to figure out the total distance that this particle, we could figure it out, but we don't have the best tools to figure out the total distance that that particle might travel on any given time period. So we'll learn some better tools later on this year. All right, we are on some other planet X, because we've destroyed Earth or something, who knows. And we're taking a stone and throwing it vertically upward, and its height after t seconds is given by this equation. The height, or a position, right? Height is a position, is 10t minus 1/2 t squared. We want to know what is the velocity of the stone after 2 seconds. So how will we figure that out?
Plug in 2 for t.
That'll tell us the height of the stone, but we want to find the velocity of that stone. So what do we need to do first? If we're given a position function and we want to find the velocity function,
Yeah.
we need to take the we got to take the derivative h prime of t, which will give us our velocity, which should be 10 minus t. And now we can evaluate that at t equals 2 to find out that the velocity of the stone is 8 meters per second. Good or no?
Good.
Okay. If we want to know the velocity of the stone after it has risen 25 meters, what do we need to do? We need to find v of some value. Well, what's that value? How do we figure out?
You set the original equation equal to 25 and solve for t.
That is exactly what we should do. We know that it's risen 25 meters, so we'll say that the height is 25. 25 equals 10t minus 1/2 t squared. And probably first we'll turn that into just 50 equals 20t minus t squared, because that'll probably make life a little bit easier for the arithmetic. Or t squared minus 20t plus 50 equals 0. And does that factor or does that not factor? I don't believe that factors, so we'll do,
I don't think so.
yeah, 20 plus or minus the square root of 400 minus 4 times 1 times 50, so that's 200 all over 2. And 400 minus 200 is 200, and square root of 200 is 10 root 2, so we got 20 plus or minus 10 root 2 all over 2, or 10 plus or minus 5 root 2. And which of those are we going to be looking at after it has risen 25 meters? Will that be 10 plus 5 root 2 or 10 minus 5 root 2?
Plus.
Common answer is plus, but nah, it's actually the minus, because what's happening here? The stone's going to go up and then it's going to come back down. So after it has risen 25 meters, that'll be the first t value. So we want the smaller t value. Right here, let's say that's 25 meters. It hits 25 meters twice, right? this one is the minus, and this one is plus. Does that make sense?
Yeah.
All right, so we're looking for v of 10 minus 5 root 2. And if we plug that into 10 minus 10 minus 5 root 2, 10 minus 10 cancels out, the negatives will cancel out, and we end up with 5 root 2 meters per second. Not much gravity on this planet, apparently.
Wait, why is it 10 minus 5 root 2?
Because our velocity function itself is 10 minus t. All right, we're looking for the velocity, so we have to use the velocity function, which was the derivative of our h function. Velocity was 10 minus t.
Oh, and when that equals.
So we're looking for the velocity at 10 minus 5 root 2 seconds.
Oh, okay.
So it's 10 minus 10 minus
10
5.
minus that time. Okay, that's time. Oh, I see. Okay.
Right, these
That
were
makes
our
more sense.
t. These were our t values at which the particle, or not particle, stone was at 25 meters. That makes
Okay,
sense.
that's
now?
right. Yeah.
Okay, cool. All right, sounds good. Let's do one more problem. This is not a motion problem. This is something that they love to throw in on the AP test in the multiple choice, if there happens to be multiple choice this year, which I'm betting that there will be. They like to just test and make sure you remember your product and your quotient rule formulas. And I'm not sure, I meant to have this slide earlier, but some reason it's at the end here. So what we want to do is for two different functions y, one of them being y equals u times v and the other being u divided by v, we want to find the derivative evaluated at 2. And all they do is just give you a bunch of these things over here. U of 2 is 3, u prime of 2 is -4, and so on. So all we're going to do is we're going to just apply the product rule. What's the product rule for the derivative of u times v?
U times the derivative of v plus v times the derivative of u.
All right, somebody memorized the stuff they were supposed to memorize or looked through their notes just now. Perfect. So if we want to find the value of this at 2, all we do is just plug in the values given to us. So u at 2 is 3. V prime at 2 is 2. V at 2 is 1. And u prime at 2 is -4. So the derivative of u times v at 2 is 2. Any issues with that?
Nope.
All right, what if it was u divided by v? Then the derivative should be v times the derivative of u minus u times the derivative of v all over v squared. And we'll just plug in the values. V is 1, u prime is -4, u is 3, v prime is 2, and v again is 1. So we got -4 minus 6, which is -10. They love to throw those in on the AP test with sorted rules. There's some other rules that we'll want to know about these, or other rules that we'll be wanting to apply with just a bunch of values given to us, but we'll worry about those when we get to those rules. Any questions or issues with that? Pretty straightforward, I hope.
All good.
All right, has anybody got any issues with derivatives of constants, derivatives of polynomials, or any other derivatives we use the power rule with, or the product rule, or the quotient rule, or the reciprocal rule?
I just have a quick question. With
Okay.
the physics stuff that we were doing before, does that come up quite a bit, or is that just kind of like
Yeah, we're going
scarcely
to do, there'll be some problems that have to do with basic motion problems. We are going to do a little bit more of it in the next week or so. but then later on, we're really going to study it quite a bit more when we start talking about integrals, because that will allow us to do a lot more work with it. And that's when things will start to sort of, those sorts of problems will start to show up more on the AP test than the more basic ones like what we just now did.
Okay.
Does that help answer your question? I mean, it's gonna happen. You're gonna have to do motion problems, but we're not gonna focus on it yet until we have a lot more tools at our disposal to make it more complicated, but also more worthwhile, because we can just do more with it. We can start with an acceleration equation and come up with the position function rather than only being able to have like a position function and find the other ones. We can go the other direction also, so eventually. Okay. Any other questions on anything we've done with the derivatives so far before we move into throwing in some trig derivatives? All right, can you see the new slides here? Derivative of sine x. Yeah, can we see that? Find the derivative of, okay,
Yep.
sine x. Okay. Well, how are we going to do this? I know some of you probably already know what the derivative of sine x is. That's which is great. You've looked it up somewhere. Somebody told you something, something, something. The question is, how do we prove that that's the derivative of sine x? How do we prove that this thing that you might already know is the derivative of sine x? How do we find it?
We can use like the basic derivative thing where we take the, what was it called? What was that thing called?
The difference quotient?
Yeah, the difference quotient. Yeah, we can do
Yeah, the limit as h approaches 0 of f of x plus h, so that'll be sine of x plus h minus sine of x all over h. Yeah? Everybody good with that?
Yep.
Okay, cool. So plug in your 0 for h and you get 0 over 0. All right, cool. What am I going to do now?
change some stuff up.
Okay. Like what?
Could you use the trig identities to expand sine of x plus h?
I could, and I will. That's what we will do. So do you happen to know offhand what that identity says? Sine of a plus
Sine of
b.
x times cosine of h plus sine of h times cosine of x.
Sine x cosine h plus cosine x sine h. Is that what you said? I think that's what you said.
Yeah.
Cool. Yep, sine x cosine h plus cosine x sine h, and then we have our minus sine x still up there at the top, all over h. All right, so now if we plug in 0 for h, cosine of 0 is 1, so this is just sine x. And sine of h is 0, so that goes away. So we have 1 plus 0, sine x plus 0 minus sine x, which is still 0 over 0. Okay, well, bummer. This is still right, but we're going to have to do some more work to it. Anybody see some more work they'd like to do with this?
You have 2 sine x's in the numerator, so you could probably isolate those.
Okay, so let's do that. Let's write the limit as h approaches 0 of, let's see, sine x times, if I factor the sine x out of that, what's left? Cosine h, and then minus 1 over h. And then I could add to that the limit as h approaches 0 of just this other term, cosine x sine h over h. You guys okay with that? So I took sine x cosine h and minus sine x, put those together as one limit, right? If I distribute this back out, sine x cosine h minus sine x over h. And then we added to it the other piece, but this is just factored out with sine x. Good or no?
Yep.
Good.
All right, let's look at each piece of this then real quick. First off, if I plug in 0 here, what do I end up with? I have cosine of 0, which is 1, minus 1, which is 0, over 0. So I have 0 times sine x, which is 0, over 0. So that's indeterminate still. And then this one, if I plug in 0, I've got cosine x times sine of 0, which is 0, over 0, which is 0, 0. So still indeterminate. But hopefully on the right-hand side, at least, we see a little something going on there.
Sine of
Sine of
h over h.
Yeah, sine of h over h. So could I separate this one into two different limits, one that's just cosine x and one that's sine h over h?
Yeah.
Yeah.
All right, well, let's do that. And that should be separated using multiplication, right? What about over here? Anybody see something good to do with that?
Cosine of h minus 1 over h.
Okay, just do the cosine of h minus 1 over the h?
Yeah.
Okay. And what about the sine x? Just leave it there?
Yeah.
Okay. And now we'll see why it was so important that we have all these rules memorized, right? The limit as h approaches 0 of sine x is sine x. The limit as h approaches 0 of cosine h minus 1 over h, that's one of our rules. What does that equal?
0.
0. And then plus the limit as h approaches 0 of cosine x is cosine x. And the limit as h approaches 0 of sine h over h is
1.
1. And so what are we left with? Just cosine x. So the derivative of sine is cosine. Good?
So you didn't need when you split it up from the red pen to the blue pen, you didn't need to keep the h over both terms? Is that like a rule that I just forgot or something?
That's just multiplying fractions. So this could be sine x over 1 and cosine x over 1, right? Remember, we're multiplying these together. So I can't put an h in the denominator of both of them because then I'd end up
Oh, I see.
had an
Because
h
the limit
squared.
rule, you have to multiply. Yeah, okay.
Right. So I didn't write the over 1, but it's there, right? So I could have chosen to put the h underneath the sine x and left this as just cosine h minus 1 if I'd wanted to. But that doesn't give us the identity that we need. So we need that h under the cosine h minus 1, and we need the h under the sine h. Good? All right. So if the derivative of sine is cosine, what's the derivative of cosine?
It's a sine.
One would hope that it's just sine, yeah? But it's not.
That would be nice.
That would be nice, but it's not the case. So let's do the limit as h approaches 0 of cosine of x plus h minus cosine of x all over h. And I bet you have a pretty good idea of what we're going to do here. What do you think we should do with the cosine x plus h? Probably expand it out. Yeah, so what's the identity for cosine of a plus b? Should be cosine x cosine h, and then what?
Minus sine x.
Minus sine x sine h, yep. And then we have a minus cosine x there. All over h. Everybody good?
Do we have to memorize those trig addition, like what
Nope.
that is, what cosine of a plus b is?
Nope, you don't need to have it memorized. When you were taking your rigorous honors pre-calculus course last year that you all took, right? Haha. You should have memorized it then, and of course you would still have it memorized, but you'll never need to have it memorized for this class.
Cool.
Yep. All right, so then we'll see that there's a cosine x in two of those terms, so we'll factor out the cosine x and split. It's going to be a very similar process. So we got h approaches 0 cosine x times cosine h minus 1 over h, and then minus the limit as h approaches 0 of sine x sine h over h. And this looks very similar, right? Make this h approaches 0 of cosine x and h approaches 0 of cosine h minus 1 over h. And on this one, make this sine x and sine h over h. And as h approaches 0, cosine x is cosine x. And this is 0 minus sine x. And that is 1. And so what do we end up with? Almost sine x. But we got a negative in front of it. Everybody good with that?
Yep.
All right, spectacular. So the derivative of sine is cosine. The derivative of cosine is negative sine. Do you need to memorize those? Yes. Will it be easy to memorize? Yes, because we're going to use them a billion times. But that's only a third of the trig functions that you should know about. We probably need to figure out derivatives for tangent and secant and cotangent too. Yeah, wouldn't you think?
Yeah.
Yeah. The good news is we have a formula for tangent x plus h, right? So could we go through and do that?
Yeah.
Yeah, we could. Anybody got a better idea?
Just put sine over cosine.
Yeah, tangent is the same as sine over cosine, right? Do you know how to take the derivative of a quotient of two functions?
Yeah.
Yeah, using the quotient rule. So we'll use the quotient rule, and we know the derivatives of sine and cosine, so we should just be able to use the quotient rule. So the quotient rule says f prime of x for a quotient should be denominator times the derivative of the numerator. Derivative of sine is, found it, cosine. So v du minus u sine x, the numerator. Derivative of v, so derivative of cosine is negative sine x, all over the denominator squared. Everybody good with that?
Yep.
All right. What's cosine times cosine?
Cosine squared x.
What's a negative times a negative? That's positive. And sine times sine is?
Plus sine squared x.
So cosine squared x plus sine squared x over cosine squared x. What's cosine squared x plus sine squared x?
1.
1. We got 1 over cosine squared x, but we'll usually write this as secant squared x. So the derivative of tangent is secant squared. Everybody good with that?
Yep.
All right. What about the derivative of secant?
Well, secant is 1 over cosine, so we can use that.
1 over cosine, right? So we should be able to use the reciprocal rule for that.
Yep.
So
Yep.
the reciprocal rule says negative derivative of the denominator. So the derivative of cosine is
Negative sine.
it's negative sine. So we got negative sine. So we'll cancel those out in a bit. And then the denominator squared. So cosine squared. And so the negatives cancel and we get sine x over cosine squared x, which is a good derivative of that. But normally the way we write these is we want to try and, if we can, keep it using this same trig function. So I could rewrite this as sine x over cosine x times 1 over cosine x. And what's 1 over cosine x?
Secant.
Secant. And what's sine over cosine?
Tangent.
Tangent. So normally we'll say the derivative of secant x is secant x tangent x. And 99% of the time, that'll be the more convenient notation for it. Everybody good there?
Yep.
All right. Only 2 to go. What about cosecant x? That's the same as 1 over sine. So once again, we'll use the reciprocal rule. Negative derivative of sine divided by sine squared. And we'll rewrite this just like the other one. Negative 1 over sine times cosine over sine, which is negative cosecant x cotangent x. Everybody good with that one?
Yeah.
Yep.
Only 1 to go. Last one is cotangent. 2 different ways we could do cotangent. What are the 2 different ways? Let's do it both ways and see that they're both the same.
1 over
Cotangent.
tangent or cosine over sine.
1 over tangent or cosine x over sine x. Either one, right? So 1 over tangent should be negative, and then derivative of tangent is secant squared x, and then tangent squared x. And let's see, if we have over tangent squared, that's like dividing, or that's like multiplying by cotangent squared, right? We'll say this is the same as secant squared x, or negative secant squared x cotangent squared x. And then let's turn that into some sines and cosines here for a second. The secant squared could become negative 1 over cosine squared. And the cotangent squared could become cosine squared over sine squared. And the cosine squareds will cancel. We're left with negative 1 over sine squared, which is negative cosecant squared. That's normally how we'll write the derivative of cotangent. So, but if we're going to do cosine over sine, we should do the quotient rule. So sine x times the derivative of cosine x, which is negative sine x, minus cosine x times the derivative of sine x, which is cosine x, all over sine squared x, which if we take the negative and the negative here and factor it out, that's negative sine squared x plus cosine squared x over sine squared x, and sine squared x plus cosine squared x is 1, so this is negative 1 over sine squared, which is negative cosecant squared x. So either way, same result. Derivative of cotangent is negative cosecant squared. Everybody good with the derivations of all 6 of those trig functions?
Yeah.
Yep.
All right. I'm going to put this slide here just so you can see them all next to each other and we can see that they're all fairly related. And then after I talk about them for 1 minute, I'm going to work under the assumption that you now have all of those memorized, because you will do that before I see you on Monday. Yes?
Yep.
Yes. All right. So derivative of sine, cosine, derivative of cosine, negative sine. Those 2 are probably pretty easy to remember. Okay. Derivative of secant, secant tangent. Derivative of cosecant, negative cosecant cotangent. So those 2 are pretty similar also, right? Secant one is secant tangent, and then the cosecant one is negative cosecant cotangent. Yeah?
Yeah.
Okay. And then the tangent is secant squared, and the cotangent is negative cosecant squared. So we can see that those are related also, similar. Hopefully.
Yep.
Cool. We might note a couple of things. One, well, really only one thing, that all of the regular trig functions, and when I say regular trig functions, I mean sine, tangent, and secant, all come out to be positive. And when I talk about the not regular ones, what I really mean is the co-trig functions, cosine, cosecant, and cotangent, all come out with a negative from their derivative. So sine, tangent, secant, the ones that don't have a co in front of them are all positive derivatives, and the ones that have the co in front of them all have negative derivatives. Easy way to help you remember which ones have positives and negatives, perhaps. Everybody see that and good with that? All right. I don't know what time we get out of class. What time do we get out of class? Anybody know? We still have time if I got over?
11:27.
Yeah, 27.
Oh, we got lots of time still. That's great. All right, let's find the derivative of tangent x over x. How will we go about doing that?
The quotient.
Quotient rule, yep. So we'll do v, so the denominator, times the derivative of tangent. We just learned that. What's the derivative of tangent?
Secant squared
Secant
x.
squared x?
Yep, so x secant squared x minus u, so tangent, times the derivative of x, which is
1.
1, so we don't even need to write the 1, all over the denominator squared, x squared. Good or no?
Yep.
All right, that's it. No simplification needed there. That is our answer. All right. Any questions? Everybody good?
All good.
All right. Secant x over sine x. Again, a quotient rule problem, yeah?
Yeah.
All right. So f prime of x should be sine x times the derivative of secant x, which is what?
Secant x, tangent x.
Secant x tangent x. So that's v du minus u secant x times the derivative of sine, which is cosine x, all over sine squared x. And it'd be nice if we could do a little bit of simplification there, I hope.
Yep.
What is secant x? Secant x is 1 over cosine. So I've got sine over cosine, which is
Tangent.
tangent. And then I've got tangent times tangent, which should be tangent squared. And then I've got minus secant x times cosine x. Well, what's secant x is 1 over cosine, so this is just cosine over cosine, or just 1. And then over sine squared x. Is that a good answer?
Isn't there an identity for tangent squared minus 1?
No, there's an identity for 1 plus tangent squared. 1 plus tangent squared is secant squared. Everybody good or no?
Is that fully simplified right there?
Sure, that's a great answer. Now, if this was the AP test and this was multiple choice, that might not be the answer they give. They might give you something like, and this is good. I would be fine with this, but maybe the answer they give is rearranged a little bit. So like I could divide both pieces of that by sine squared x, and then tangent squared in the numerator would become sine squared x over cosine squared x, with the sine squared x down there still, minus 1 over sine squared x, and those could cancel. So you might see something like secant squared x minus cosecant squared x, right? This would be a fine answer too. And if you're looking at a multiple choice question, they might write it like this. They might write it like this. They might write it at any stage in between there. They might write it like this. And you never really know what they're going to do. So I got a question sent to me in the chat privately. So you're going from here to here, going from just the original f of x to f prime of x. Yeah, so that's using our quotient rule. That's quotient rule from what we learned yesterday, I think. And so that's v, that's our denominator is sine x. And then the derivative of the u, the derivative of the numerator, the derivative of secant is secant x tangent x, minus the numerator secant x times the derivative of the denominator, cosine x, over the denominator squared. So v, I'll write it here, v du minus u dv over v squared. Does that help? Cool. All right. We got lots of problems left that I wanted to do, but let's see if we can find a derivative of secant squared x.
Did you use the product rule?
Yeah, we'll have to use a product rule for this. So our product rule, we'll change this into secant x times secant x. And so now we can use the product rule for f prime of x. It should be secant x times the derivative of secant x, which is secant x tangent x. Right, u v prime plus v u prime, which will be plus secant x times secant x tangent x. And we have 2 secant squared x tangent x. Everybody good with that?
Yep.
All right, cool. That's not necessarily how our answer might be written. We could write it as 2 sine x over cosine cubed x for 1, right? Secant squared would drop a cosine square into the denominator, and tangent would drop another cosine. But either of those is fine. Doesn't really matter to me, but just be able to do them both. All right, let's find the fourth derivative of sine x. And we'll probably stop after this one because we're getting close to the end of our time here. So f prime of x should be what?
Cosine x.
What about f double prime?
Negative sine x.
Negative sine, or yeah, negative sine x.
Yep, derivative of cosine is negative sine. What about f triple prime?
Negative cosine.
Negative cosine, good. And what about the fourth derivative? So you go right back
Sine
to
x?
positive sine of x, exactly. And so we'll note that if we take enough derivatives of sine, it's going to come right back to being sine again. It's just going to repeat. And same with cosine. If I were to do the same with cosine, we'd start here. This would be our original function. We go negative sine, negative cosine, positive sine, and then that next derivative would be just cosine again. Everybody see that?
How do you differentiate from negative sine x to negative cosine x? I'm just missing something there.
So this negative is just a -1 coefficient out in front.
Oh, so you just move the constant out.
It's just
I
a
see.
constant. So yeah, the constant just stays, and you take the derivative of sine. Same here, the constant negative just stays. We take the derivative of cosine, so it becomes negative sine. Or just sine.
Okay.
All right. Any other questions on anything we've done today? No?